Welcome to day 6 of Master AI in 30 days. We've explored mathematical foundations, machine learning, deep learning, and natural language processing. Today, we turn our attention to how computers see and understand visual information, computer vision. Vision is humanity's dominant sense. We navigate the world primarily through sight, teaching machines to see, to process images, to understand visual scenes. This is one of AI's most impressive achievements and most impactful applications. Today, you'll understand how images are represented digitally and processed by neural networks. You'll explore advanced CNN architectures that push the boundaries of image recognition. You'll dive deep into object detection, not just classifying images, but localizing multiple objects within them. You'll understand image segmentation and visual understanding. You'll explore modern architectures like vision transformers that challenge CNN dominance. By the end of today, you'll understand how autonomous vehicles see roads and obstacles, how medical imaging systems detect tumors, how satellite systems analyze terrain, how security systems recognize faces. You'll understand the technology enabling these transformative applications. Let's see what computers can see. Here's exactly what we'll accomplish today in computer vision. First, we'll understand how images are represented in computers as matrices of pixel values. We'll explore basic operations like convolution, pooling, and their effects on images. This foundation helps you understand what CNNs do and why they work so well for vision. Second, we'll study advanced CNN architectures. ResNet introduced skip connections, enabling deep networks. Inception used multi-scale processing. EfficientNet optimized scaling across multiple dimensions. Understanding these architectures reveals design patterns for building vision models. Third, we'll tackle object detection, one of the most commercially important computer vision tasks. Instead of just classifying entire images, object detection locates and identifies multiple objects. We'll study YOLO's real-time approach, RCNN's region-based methods, and modern unified approaches. Fourth, we'll explore segmentation, assigning semantic labels to image regions or individual instances. Semantic segmentation classifies pixels into categories. Instance segmentation separates individual objects. Panoptic segmentation combines both. These enable applications from medical imaging to autonomous vehicles. Finally, we'll examine vision transformers and multimodal models that combine vision and language. These represent the current frontier of visual understanding, challenging the dominance of CNNs with attention-based approaches. After today, you'll understand the computer vision systems transforming industries. Understanding how computers represent images is foundational. Images are matrices of numbers, nothing mystical, just numbers. A grayscale image is a 2D array where each element represents the brightness of a pixel. A 256 256 grayscale image has 65,536 numbers, each between 0, black, and 255, white. A color image is a 3D array with separate channels for red, green, and blue, RGB. A 256x256x3 color image has 196,608 numbers. Your 12-megapixel phone camera produces arrays with 12,000 pixels per channel. Neural networks process these arrays. Convolutional layers apply filters across the spatial dimensions. Pooling layers reduce spatial dimensions. At each layer, the spatial structure of the image is preserved. Nearby pixels influence each other, capturing local patterns. This is why CNNs work so well for vision. They are structurally suited to exploit the spatial structure of images. It's crucial to recognize that images are just numbers. When you apply filters, compute attention, or transform representations, you're doing mathematical operations on numbers. This demystifies computer vision. It's math applied to arrays, nothing more magical than matrix multiplication and activation functions. Different image formats store data differently. JPEG uses compression, losing some information. PNG is lossless. RAW files store raw sensor data. But fundamentally, they're all arrays of numbers representing light intensity. After AlexNet's breakthrough in 2012, the field evolved rapidly. Let me highlight architectures that shaped modern computer vision. ResNet solved a critical problem. As networks got deeper, training degraded. Error rates decreased, then increased. Networks weren't learning useful patterns, they were getting worse. ResNet introduced skip connections, residual blocks, allowing gradients to flow directly through networks. If a block doesn't help, the skip connection preserves information. This enabled networks with 100 plus layers, far deeper than previous records. The insight make networks so deep that learning becomes the bottleneck, not depth. Inception, GoogleNet, used a different approach, parallel paths processing at multiple scales simultaneously. Instead of just stacking layers, different branches use 1x1, 3x3, and 5x5 convolutions, capturing patterns at different scales. Outputs concatenate, giving the network diverse feature representations. This multi-scale processing proved more efficient than simply going deeper. EfficientNet systematically studied how to scale networks. Networks can scale in depth, more layers, width, more channels, or resolution, larger input images. Previous work scaled one dimension, but EfficientNet showed that balanced scaling across all three yields better efficiency. An EfficientNet model optimized for performance achieved better accuracy with fewer parameters than previous architectures. Modern architectures combine these insights. Skip connections are standard. Multi-scale processing is common. Systematic scaling guides design choices. The field has matured from stack more layers to principal design optimizing efficiency and accuracy. Object detection goes beyond classification. Instead of answering what's in this image, it answers what objects are where. For each object, the model must identify its category, car, person, dog, and localize it with a bounding box defining its position and size. An image might contain multiple objects of different sizes partially occluding each other. The model must handle all these complexities simultaneously. Challenges include scale variation. Objects vary dramatically in size. Occlusion means some objects are partially hidden. Cluttered backgrounds confuse models. Different aspect ratios. Some objects are tall and thin, others wide and flat. A good object detector handles all these variations. Applications are everywhere. Autonomous vehicles detect pedestrians, cars, bicycles, and obstacles. Security systems detect intruders. Retail systems count products on shelves. Medical imaging detects tumors and abnormalities. Sports broadcasting tracks players and balls. Drones survey terrain. Object detection enables these applications. The field evolved through approaches. RCNN examined candidate regions one by one using CNNs, slow but accurate. Fast RCNN and faster RCNN improved efficiency. YOLO treated detection as regression, directly predicting bounding boxes and class probabilities, fast but less accurate initially. Modern approaches balance speed and accuracy. Single-stage detectors like YOLO are real-time. Two-stage detectors like RCNN are accurate. The gap narrows as methods improve. Understanding object detection reveals how to structure problems so neural networks can solve them efficiently. YOLO revolutionized object detection by framing it differently than previous approaches. Instead of region-based detection, YOLO treats detection as a regression problem. The key idea: divide the image into an SXS grid. For each grid cell, the network predicts B bounding boxes and class probabilities. The output is a tensor, grid cells predictions per cell, typically 7 x 7 x 30 for VOC dataset. Everything happens in a single forward pass through a CNN. Why the name "you only look once"? Traditional object detection systems examine multiple regions, running classification on each. YOLO looks at the entire image once, predicting all objects simultaneously. This is incredibly fast. YOLO can process 4590 images per second, enabling real-time applications. Previous systems processed only a few images per second. The trade-off: YOLO struggles with small objects and objects close together in the same grid cell. Multiple objects in one cell mean only one prediction per cell, causing missed detections. But for many applications, especially video, YOLO's speed vastly outweighs this limitation. Modern YOLO versions, YOLO v3, v4, v5, v8, improved accuracy and efficiency. They use better backbones, multi-scale predictions, improved training techniques. YOLO v8 achieves near SOTA accuracy at real-time speeds. YOLO's influence extends beyond object detection. Its efficiency and elegance inspired approaches in other domains. It demonstrates that simple, fast approaches can work remarkably well when well designed. Image segmentation goes deeper than object detection. Instead of bounding boxes, you assign a category to every pixel. Semantic segmentation labels pixels without distinguishing individual object instances. For an autonomous vehicle, the goal might be which pixels are road, which are pedestrian, which are vehicle, which are building. All cars are labeled the same regardless of how many cars are in the image. Instance segmentation goes further, distinguishing individual objects. Each car gets a unique label or color. This is harder. The model must detect object boundaries and identify which pixels belong to the same object. For medical imaging detecting tumors, instance segmentation separately outlines each tumor. Panoptic segmentation combines both approaches. Stuff classes like road, sky, water use semantic segmentation, no instance distinction. Thing classes like people, cars, animals use instance segmentation, separate instances. This comprehensive approach gives rich scene understanding. Applications are transformative. Medical imaging uses segmentation to outline organs, tumors, and abnormalities precisely. Autonomous vehicles segment the scene into drivable regions, obstacles, and other categories. Satellite imagery segments land use, forests, urban areas, water bodies. Agricultural systems identify crop health regions. Robotics use segmentation for manipulation and navigation. Architectures for segmentation typically use encoder-decoder structure. The encoder, usually a CNN, downsamples and extracts features. The decoder upsamples and produces per pixel predictions. Skip connections from encoder to decoder preserve spatial information lost during downsampling. UNet, popular for medical imaging, exemplifies this architecture. Vision transformers, VIT, challenge CNN dominance by applying the attention-based transformer architecture to images. The key innovation, instead of convolutional filters processing local neighborhoods, divide the image into patches. A 224x224 image becomes 196 patches of 16x16 pixels each. Embed each patch as a sequence token. Apply standard transformer processing. Each patch attends to all other patches, enabling long-range interactions without the sequential limitations of CNNs. Why is this powerful? CNNs have locality bias. Each filter only sees a small region. Features must combine across layers to capture long-range relationships. Transformers enable direct long-range interactions from the first layer through self-attention. Patches farther apart can directly communicate. Performance shows vision transformers are competitive with CNNs. On ImageNet classification, VAT matches or exceeds ResNet and EfficientNet. When trained on larger datasets, like ImageNet 21K, VAT often outperforms CNNs. The advantage grows with scale. The relationship between model size and performance follows different scaling laws than CNNs. Advantages of VIT: better at capturing long-range dependencies, more parameter efficient at large scales, potentially more interpretable attention visualizations, benefits more from scaling. Disadvantages: require more data for training, less inductive bias for spatial structure, higher computational cost per token. The current consensus: transformers and CNNs will likely coexist. CNNs have strong spatial inductive biases useful for vision. Transformers have flexibility valuable for large-scale learning. Hybrid architectures combining both appear promising. Computer vision enables transformative real-world applications. Let me highlight major areas. Autonomous vehicles rely entirely on computer vision. Cameras provide input to perception systems, identifying roads, pedestrians, cyclists, vehicles, traffic signs, lane markings. Object detection locates obstacles. Semantic segmentation identifies drivable regions. Instance segmentation tracks individual obstacles. Temporal reasoning across frames predicts movements. Vision failures cause accidents. This application requires extraordinarily reliable perception. Medical imaging uses vision for diagnosis and surgery assistance. CNNs detect tumors with accuracy rivaling radiologists. Segmentation outlines organs and abnormalities precisely. Retinal imaging analyzes diabetic complications. Pathology slides identify cancers. X-ray and CT scans detect fractures and abnormalities. Computer vision augments doctor expertise, catching what humans might miss, enabling earlier treatment. Satellite imagery covers Earth continuously, generating petabytes of data. Computer vision analyzes this for climate monitoring, disaster response, urban planning, agriculture, illegal deforestation detection. Object detection locates ships, cars, buildings. Segmentation identifies land use, crop types, water bodies. Change detection tracks urbanization and environmental degradation. This application processes massive scale imagery. Face recognition powers modern security and convenience. Unlock phones with your face. Identify people in photos. Security systems recognize travelers. Biometric authentication enables contactless payment. This technology raises privacy concerns but demonstrates vision's capabilities. Other applications: sports analytics, tracking players and balls, quality control, defect detection, retail, inventory, people counting, agriculture, crop health, pest detection, drones, navigation, monitoring, search, image indexing, and retrieval. Vision has become foundational infrastructure in modern systems. Multimodal AI combines vision and language, enabling richer understanding and more natural interaction. Image captioning describes images in natural language. A model takes an image and generates descriptive text. A brown dog playing fetch in a park. This combines CNN vision processing with RNN or transformer language generation. Applications include accessibility, describing images for visually impaired, content management, auto tagging, and understanding. Visual question answering answers questions about images. Given how many people are in the image or what color is the car, the system first analyzes the image, then answers. This requires visual understanding to locate relevant objects and language understanding to generate answers. VQA is harder than simple captioning. It requires addressing specific questions about images. CLIP, contrastive language image pretraining, learns shared embedding space, where images and text with similar meaning have similar vectors. Train on large pairs of images and text descriptions. An image of a dog and the caption "a dog" should have similar embeddings. A random image and "a dog" should have dissimilar embeddings. Learn embeddings such that image-text pairs that actually go together are closer than random pairs. This enables image retrieval by text search. Enter a description and find matching images. These models enable new interactions. Show me pictures of red cars from last summer becomes feasible. Image search becomes more intuitive and semantic rather than relying on metadata tags. Accessibility improves. Systems can describe images to visually impaired users more naturally. Content understanding improves. Systems comprehend images in context of text. The future likely involves larger multimodal models understanding images, text, audio, and video jointly. GPT-4 demonstrates this. It accepts both image and text input, answering questions about images. This represents progress toward more integrated AI understanding multiple modalities. Transfer learning is crucial in computer vision, making powerful models accessible. ImageNet pre-training became standard. Models trained on 1.2 million labeled images from 1,000 categories learn rich visual features. These features transfer well to new tasks. Fine-tune the model on your specific dataset. Maybe medical images with 10,000 examples. The model starts with good representations and adapts quickly. This dramatically reduces resources needed. Training a ResNet 50 from scratch requires 100 plus GPU days on ImageNet. Fine-tuning takes hours on a single GPU. Small datasets that would fail from scratch training succeed with transfer learning. A model trained on 1,000 examples typically fails. With ImageNet pre-training, transfer learning works with 1,000 examples. Few-shot learning becomes possible. With pre-trained features, models adapt to new categories with minimal examples, sometimes just a few per category. Show a model 5 examples of a new animal species, and it can classify that species with surprising accuracy. This is because ImageNet pre-training taught universal visual features. Recent work shows vision models trained on larger datasets, ImageNet 21K with 14 million images, or JFT 300K with 300 million images, offer even better transfer. Bigger pre-training datasets, better transfer, better performance on downstream tasks. The lesson: don't train from scratch, use pre-trained models. The computational and data advantages are enormous. This democratizes vision AI. Advanced capabilities become accessible without massive resources. Despite impressive capabilities, computer vision faces important challenges. Robustness is critical. Adversarial examples, Tiny pixel-level perturbations imperceptible to humans cause misclassifications. A stop sign with carefully placed stickers becomes an unrecognizable object. This is concerning for autonomous vehicles and security systems. Distribution shift, when test data differs from training, causes failures. A model trained on clean images fails on noisy or low-resolution images. Building robust systems remains difficult. Interpretability. Why did the model classify this image as a cat? This is unclear. Attention visualizations and saliency maps provide hints but don't fully explain decisions. In medical imaging, doctors need to understand model reasoning to trust and build on its suggestions. Interpretability remains an open challenge. 3D understanding. Images are 2D projections of 3D scenes. Autonomous vehicles need 3D understanding. 3D object detection, scene reconstruction, and 3D semantic understanding are harder than 2D but crucial for applications. Combining multiple camera views, depth sensors, and temporal information helps but remains challenging. Efficiency. Large vision models consume enormous memory and computation. Deploying ResNet 152 on a phone drains batteries. Edge devices need lighter models. Quantization using lower precision, pruning, removing parameters, knowledge distillation, training small models to mimic large ones, and neural architecture search, automatically finding efficient architectures, all help, but perfect efficiency remains elusive. Addressing these challenges is critical for deploying vision AI responsibly and effectively. Manually designing network architectures requires expertise and experimentation. Neural architecture search automates this process. NAS treats architecture design as a search problem. Define a search space of possible operations, convolutions of different sizes, pooling, skip connections, activation functions. Define objectives. Maximize accuracy while minimizing parameters or latency. Search for architectures balancing these objectives. Search methods include evolutionary algorithms, maintain population, mutate good architectures, reinforcement learning, agent designs architectures, rewards based on performance, and gradient-based methods use differentiable relaxations enabling gradient descent. Early NAS methods were expensive, requiring thousands of GPU days. Efficient methods like darts now search in hours. NAS discovers surprising architectures. EfficientNet emerged from NAS optimizing for accuracy and parameters. Found architecture balances depth, width, and resolution differently than human intuition. Mobile nets emerged optimizing for mobile efficiency. Small, fast, still accurate. Benefits. NAS discovers non-obvious designs. Finds architectures optimized for specific constraints. Power consumption, latency, memory, adapts to datasets and hardware. An architecture optimal on ImageNet might differ from one optimal on medical images or edge devices. Limitations. NAS is computationally expensive, though improving, assumes differentiable or simulatable environments, may miss architectural innovations humans would invent. NAS works best combined with human expertise. Humans define search spaces and objectives. NAS explores efficiently within those constraints. The future likely involves more automated architecture design. As NAS improves, handcrafted designs might become less common. Computer vision continues evolving rapidly. Several directions are shaping the future. Unified models attempt to handle multiple vision tasks: classification, detection, segmentation, depth estimation with a single architecture. Rather than building separate models for each task, unified models solve multiple tasks simultaneously, leveraging shared representations. This is more efficient and potentially more capable. Self-supervised learning reduces label requirements. Instead of requiring manually labeled data, learn from unlabeled data by constructing self-supervised objectives. Predict image rotations. The model must understand content. Mask and in-paint regions. Contrastive learning. Pulling similar images close, pushing different images apart. These objectives avoid expensive manual labeling while learning useful representations. Combining self-supervised pre-training with minimal labeled fine-tuning achieves strong results. 3D and video understanding are advancing. Beyond classifying static images, understanding 3D scenes and temporal dynamics is crucial for robotics, autonomous vehicles, and augmented reality. Point clouds, volumetric representations, 4D tensors, space and time, and attention mechanisms enable better 3D and video understanding. Foundation models are emerging. Very large models trained on massive diverse data that work remarkably well across vision tasks with minimal adaptation. Clip connects images and text across millions of examples. Flamingo processes images and text jointly. These models show zero-shot capabilities, performing tasks without task-specific training. The foundation model paradigm might reshape how vision AI is built and deployed. The field evolves from task-specific models to increasingly general-purpose, capable systems requiring less task-specific data and adaptation. Tomorrow is day 7, Reinforcement Learning Basics. We shift from supervised learning, learning from labeled data, to learning from rewards and penalties. Reinforcement learning involves an agent interacting with an environment, taking actions, and receiving rewards. Unlike supervised learning with labeled correct answers, RL learns by trial and error. The agent explores, collects rewards, and gradually improves policy. Applications include game playing, AlphaGo, AlphaZero, robotics, manipulation, navigation, autonomous driving, and optimization. We'll cover the fundamental concepts: states representing agent perception, actions available, rewards guiding learning, policies determining action selection, value functions estimating how good states are, and Q learning enabling learning optimal policies. We'll explore policy gradient methods that directly optimize action selection. We'll see how RL differs fundamentally from supervised learning: delayed rewards, exploration, exploitation trade-offs, non-stationary environments. We'll discuss applications: game playing AIs surpassing human experts, robots learning manipulation from pixels, autonomous systems making sequential decisions, but also challenges: sample inefficiency, requires enormous interactions. Exploration difficulty, must balance trying new actions versus exploiting known good actions. Credit assignment, which action caused rewards after many steps. Excellent work today. You now understand how computers see and understand visual information. Tomorrow, we explore decision making and learning from rewards. See you then.